All right, so we're looking at 13b now. This is Newton's laws of motion. So there's quite a bit of physics in this. So I want to spend a little bit of time at the start just explaining what's going on. And then we'll get into working through the questions. So this is the solutions that are also up on Canvas for your notes. So first one is knowing Newton's laws of motion. There are three. So these are named after Sir Isaac Newton. The first one we're going to look at is the idea, this isn't a law, but actually just the idea of momentum. So momentum equals mass times velocity. And basically, once something is moving, it has a certain momentum, right? So if you are moving, if you roll a gigantic snowball down a mountain, you have a huge mass with a fairly, high velocity, so it has a lot of momentum. Whereas if you roll a cat, down a tiny slope, it won't have as much momentum because it doesn't have as much mass, unless the cat's going very fast, in which case it does. So an example of something with a very high momentum but a small mass would be a bullet. So a bullet has a very small mass but a high velocity, so it has a lot of momentum. That's why it can go through you. So we represent momentum by the letter P, sometimes done as a little p or a symbol like a little rounded p. But P equals mass times velocity, P equals mv. And the units are important here. Mass is always in kilos and V is the velocity. It's in meters per second, or written in the physicsy way as meters second to the -1. So there are three laws for Newton's laws. The first one is the law of motion. So it basically states that if something, if an object is stationary and nothing happens to it, it will stay stationary unless another external force occurs, and then it will move. If an object is already in motion, if no other force acts on it, it will continue in that motion forever. So obviously in our world nothing does that because things are operated on by gravity and air resistance and things like that. So that's why nothing just travels in a straight line forever. Newton's second law of motion is F equals ma. So this is the idea of force being linked to the mass and the acceleration of an object. And Newton's third law of motion is that if one particle exerts a force on a second particle, then B exerts a collinear force of equal magnitude and opposite direction. Basically, if you have something exerting a force, the other thing that it's exerting the force on will exert a force back. So the classic example of that, if I just get a nice screen up here, is standing on the earth. A person exerts a certain force called a weight force down. This weight force, Fg, is a force that is mass times gravity, m times g. Now, in order for that person to not sink into the ground and, be swallowed up and die, there is actually a force pushing back up, the earth pushing back up on the person. This is what we call our reaction force, R. And in order for this person to stay where they are, the reaction force has to be equal to the force being that's down, so that our person stays on the level ground. So this is an example of Newton's third law, where you've got a force going up, a force going down, and they're equal. Okay, so we don't have any motion. So when we look at the second law, F equals ma, which is very useful, F represents the force, m is the mass, and a the acceleration. So if you are putting notes in, this is our third law. It basically is equal and opposite forces. The first law is the one where if we have an object that's traveling, it will go on forever unless we have something happen like some other force. If we have another force occur, then that little object's going to fall. Otherwise it will keep traveling. But F equals ma, the second law, is probably the most important one we're going to look at today because it has two forms. It's got the plane form and the vector form. Now you can tell this just by the bold or by the tildes, but you need to know that acceleration needs to be in meters per second squared and that force is in newtons N, and that m is in kilos. So it's very important that all of your units are correct. You're either going to get a force that is like 8 newtons, something like that, or you're going to get a force that's a vector, so 2i plus 3j, something like that. It really just depends on the context. So knowing that, last thing that we need to look at, With normal reaction force, I've already shown you what happens when you have a person standing on the earth. So that's represented by this diagram here. No vertical motion, a push of the earth against the person. There are two situations that differ from this, and that's if you imagine something being on a platform. So imagine that you've got two situations. You're in a lift, right? So you've got a person in a lift. This lift is going down. This lift is going up. Now I want you to think, when you're in a lift, in which situation do you feel heavier? I'm just going to draw weight forces down here, mg. M is the mass of the person, yeah? Alright, you generally feel heavier when the lift is going up, because it's like you're pushing into the floor, right? Sometimes if the lift goes down really suddenly, you almost like come off the floor, you seem lighter. So because you seem lighter, the reactive force of the lift against you actually reflects that. So the reactive force R, instead of being mg, actually ends up taking into account the acceleration of the lift. So instead of this being what it would normally be, which is mg, when the lift's going down, you actually seem a little bit lighter. So it's not just g, it's a minus g, the acceleration of the lift. This one here, when the lift is going up, you sort of push down into that lift a little bit more. So this reaction force, rather than just being equal to the one going down, this mg force going down, this is actually a little bit heavier, g plus the acceleration of the lift. So you've got two situations here. This is when you've got a lift or a platform moving. Oops. So it's just worth knowing, and in your mind knowing the one that makes you seem heavier is the one that has the g plus a. The one that makes you feel lighter is the one where you've got a minus g. So think about, remember, the lift going down seems to go away from you. You seem to like, it falls away from you. You seem lighter. So that's the two situations here with the lifts. The other one is looking at forces on a slope, which is the idea of cos thetas and sine thetas and things like that, which we're going to look at. Last thing here with the theory is something called sliding friction. Now I'm going to draw a very detailed picture here of a surface in black or blue with like a car or something. Woo! It's not terrible. Okay, and we've got a weight force, Fg equals m times g. We've got a reaction force. Now in this case, it's just a car sitting there. It has to be equal, okay, because the car's not bumping up and down. We have a driving force, usually in the car, which is supplied by the engine. And if we have a driving force, we usually have two other forces that may be combined together. One of them is air resistance, and one of them is road friction. Now we're actually going to combine those together into friction, which I'm going to call Fr. And Fr has a really neat relationship. I'll draw that again. It's mu times R. Now the reason for that is R represents the mass of the object, yeah? So essentially this R is really just the mass of the object. It's the weight, actually. Mg is the weight. Depending on where you are, if you're on the moon, G is different, so you have a different weight. So this mu is a constant that tells us basically how rough the surface is. So if you have a really rough surface, it's going to be bigger, and if it's really smooth, it will be smaller. So you can see here we've got metal surfaces. This would be the little mu that you have. Mu is the constant in front of the R. So metal surfaces very small because there's not much friction, but as you get to things that have a lot of friction, mu gets really big. So two things actually affect your friction. One of them is this mu, this affects friction. The other one is the mass, or actually, to be more specific, the weight. So those two things. If you have a really heavy object, your friction will be big. If you have a really rough surface but not very heavy object, friction will be big. If both of these things are big, very rough and heavy, then friction will be very big. So these two things come into play for friction. So we're going to look at some questions now where we look at the idea of all of these things. So first thing we've got is momentum, and these are the questions in your book. I'm just going to chuck this here. So question 1 says find the momentum for each of the following. Momentum has to be in kilometers per second. They're the units. So you have to make sure everything is in kilos and meters per second. This one is not in kilos. 0.3 kilos would make it in kilos. And it's also 3 centimeters per second, which is the same as 0.03 meters per second. And that's because you're dividing by 100 for centimeters to meters. So the first one says find the momentum. So for A, P equals m times v. So it's going to be 2 times 5, so 10 kilogram meters per second. And for B, 0.3 times kilos times 0.03. So it's 9. And then you've got 1, 2, 3. 1, 2, 3. This will be kilometers per second. So that's finding your momentum changes. The next one that you've got after that is find the change in momentum. Now change in momentum is looking at the difference between the two different momentums. So you're basically looking at final momentum minus initial momentum. Oops. Okay. So if we look at the first one, we've got, this is our initial momentum, this is our final momentum. So basically your change in momentum is P final minus P initial. So, oops, so it would be 3 minus 6 or -3 meters per second. And that makes sense because you started at 6 meters a second and then it became 3 meters a second. Now that is actually its velocity. It's not the change in momentum, because your change in momentum, and actually really I shouldn't have used P's here. Your change in momentum is going to be this velocity, the change in velocity, times mass. Because remember that P equals mv. So we know this is -3. It's a 10 kilo mass, so it's -30 kilogram meters per second. So again with this one, you've got change in velocity is final minus initial, so it's a 4 meter per second. It's a gain. So change in momentum is that velocity change times the mass, which is in this question 10 kilos. So it's 40 kilometers per second. And the last one, change in velocity, final minus the original. Here you can see this becomes 9 because when you subtract the negative you get a positive. And the change in momentum is going to be 9 times 10, so 90 kilogram meters per second. So 3 very different results, even though it's just the same numbers, 6s and 3s. Actually, that's a 10. But these two, but the sign is what affects the difference in the momentum. So -30, 40, and 90. The next one is finding weight. Weight is easy. Weight is just the weight equals mass times gravity. So if we're looking in this example here where you've got a 5 kilo bag, mass has to be in kilos, gravity is 9.8 meters per second squared. Or in this case, oops, excuse me, we're looking for mass and weight, so it's newtons. And yeah, you just multiply them together. So 9.8 times 5, it's a 5 kilo bag, so it's 49. A 3-ton tractor, because this has to be in kilos, it's 3,000 kilos. 3,000 times 9.8. Now often you might actually keep these things in terms of G. So for example, if you had an 80 kilo person, that is their mass. Okay, that's what they're made of, like all the atoms and stuff that constitute them. But their weight would be 80 G. or 80 times 9.8. So you can look at it in terms of G as well if you want to leave it that way. It can get confusing if you have grams, but that's why we want to use kilos all the time. All right, next one is a force of 10 newtons acting on a particle of m kilos produces a particular acceleration. Find the value of m. Now, the red flag with this is if you see something, a question, that mentions force and acceleration, you straight up are going to use F equals ma, because that is the link between them. All right, so as soon as I see that, I just write this down. I look at this, I can see the force is 10. I don't know m, and I know a is 2.5. So now it just becomes a straightforward matter of doing 10 divided by 2.5, which you can see has been done here. Oops. Which gives you 4. Okay, so 4 kilos. So that's it, you're just using F equals ma. With this next one, 8, we're looking at a slightly more complicated situation here, which is the parachute person. So we'll have a look at this one with a picture. Now the physics in here, it really is just helped by drawing pictures, I find. So we've got a person parachuting, there's my person with parachute, and they have a mass of 75 kilos. 75 kilos represents a weight of 75 g, okay, or 75 times 9.8. The parachute only partly opens. They accelerate with a acceleration downwards of 1 meter per second. Oops. Well, do that again. 1 meter per second squared. What upward force must her parachute be providing? So we don't actually know what that is. All right. Now you can see I've got a force, because that's in newtons. I've got an acceleration. So I'm probably going to use F equals ma. So I'm going to look at the downward stuff going on here. So force equals mass. She's 75 kilos, okay? So you might like to write, oops, her mass here as well. So you can put that in. Now, there's a little bit more going on here than the F, than just this, but I'm going to change it in a second. And the acceleration is 1 meter per second squared. Okay, now the total force here is often what we call a net force. So normally you'd think, well, the only thing I have here is this, but it's not. You also have another force, which we might call P. P for parachute. So if we look at that, in this diagram, we actually have two things happening. We have the parachute person going down. I'm defining acceleration to be positive in this direction, yeah? But we have this countering force. So this is the total force that's acting on the person, or what we would just call the net force, the overall force. Right. So we have this situation. So looking at that, we've got here all we've done is we've actually found 75 times 9.8, which is 735. So we've got 735 minus P equals 75 times 1, like that. And so that means that P equals, I'm just rearranging, 735 minus 75, and this is newtons because it's a force. So that's why we've done that here and ended up with 660 newtons. So the big thing here was to look at not just the F being the only thing you can see, but what is the overall or net force that's occurring or happening to that person. So that's where I get this subtraction part from here. All right, it comes from the down force being positive, I define positive in that direction, minus the force in the other direction. That's what's going on. All right, so 660 I should write there. Okay, so next one, we've got a particle. This one is a similar thing. You know, you see mass, you see some force stuff going on. Now this one is a situation where it's not going to be scalar. You'll notice here that your force was scalar, 660 newtons. We're actually going to do one, next one, where we've got a vector. So we've got two forces. We've got a 10 kilo force. Immediately in my head I see that as a mass. I've got two forces. Immediately in my head I say I've got to add them together because there's going to be a total force. Find the acceleration. I've got a mass, I've got an acceleration, and I've got a force. So straight away I think this is F equals ma. But what you do notice is that the force here is given as a vector. So it's the vector version of this. It means acceleration will be a vector. We've got m equals 10. We've got our force vector is actually the combination of two vectors together. This one and the other one. So in the I and j direction, we have 8 plus 2, which is 10i, and 2 minus 6, which is minus 4j newtons. That's our force, our mass. So now we just chuck everything into the formula. I'm not going to bother with the newtons because I just remember to add it. And rearranging, 10 comes underneath, I minus 4 on 10j, or if you want to be pretty about it, minus 2/5 of j. And that's my acceleration, in meters per second squared. So it's actually a vector, and you'll see here, same thing, I just haven't got units, but it is a vector that you're going to get. For 19, this is the reindeer. Good question. Okay. You need to draw a picture for these. I feel like this is just seeing, yep. Okay, so we've got to look at a diagram for this because it is important to draw this up. So a reindeer, a heavy sled, there's a lot going on. All right. First thing, we've got a reindeer. And a heavy sled. This is my sled. And a reindeer. Oh dear. Oh dear. Woo. Pulling a sled. Okay, so we've got a mass of 300 kilos. 300 kilos times g is the weight. 300 times gravity. Okay, so that gives you the weight. The reindeer exerts a horizontal force of 600 newtons on the sled. So the reindeer is pulling 600 newtons, 300 g newtons down. The sled is not bumping around up and down, but it does say here the resistance to the sled's motion is 550 newtons. I always like to put a little arrow that's not connected to anything that tells me the direction of motion as well. And you'll remember that there has to be a reaction force. Now the reaction force here, because there's no other vertical stuff going on, is going to be actually exactly the same as this one. So R will be 300 g newtons. If the sled's initially at rest, find the velocity of the sled after 3 seconds. Now this last part here makes me think of Suvat, right? Because this makes me think U is 0, V I don't know, T is 3. In order for you to work with Suvat, you need to know 3 things. Now I only know 2 things. But I do know, I've seen the word mass here, and I've seen some force stuff. So I'm actually going to use F equals ma for a first part. That's going to give me A, and then once I know A, I know 3 things, and then I'll be able to find the velocity. That's the thought process that goes on here. So first thing is, let's focus on the force. So we need to know what the net force is. Okay, so our net force is your forward force, or in the direction of motion, subtracting your force against motion. So overall, you've got a 50 Newton force going in the direction of motion. F is 50. Your mass, it's a 300 kilo mass. Not 300 G, okay, just mass. So it's just the 300 times A. That means that A is 50 over 300, which gives you 1/6 meters per second squared. Now we know U equals 0, V equals, we don't know, T equals 3, A equals 1/6. So we can use V equals U plus AT. We can sub in the U, which is 0. A is 1/6. T is 3, so it's 1/2 meters per second for velocity. And here I've sort of just skipped that a little bit. I've actually here I've done it very differently. I used acceleration, but you could do the dv/dt here as well and integrate. Actually, it's a little bit more work. It's probably easier just to use suvat. All right, cool. So that's the reindeer, 0.5 meter per second for velocity. The next question, we're looking at a particle with 3 forces. Now I can probably just go through this with you. You can see the particle's acted on by 3 forces, F1, F2, F3, and they're given, except for F3. And the acceleration of the particle is 0.6 I. It's a 16 kilo particle. So first thing is to think F equals ma, right? There's the mass, there's the acceleration. Multiply them together, and you end up with those two things, 16 times 0.6, contributing to our final answer here. So that's going to be the ma part. The force part is the 3 vectors added together. The one you're given, F1, the F3 that we aren't given, and the F2. So all of this, these 3 forces equal 16 times 0.6 I. Okay, so that's what's happening here. We've actually just simplified all of this, just turns into negative 10 I. Because negative 10, the minus 15 plus 16 gives you 1j. It just simplifies. So this thing equals 16 times 0.6. And then with a bit of rearranging, you'll find that this part here and this part here is 9.6. Take all this other stuff over, and then you end up with F3. So it's basically just rearranging F equals ma for that one. This one's a classic one. They always put these on exams, I find. So you've got a lift operator of 85 kilos standing in the lift. The lift is accelerating downwards. Okay, it's a downward lift, so you appear to be lighter. So this is this formula. And you just put everything in. The lift acceleration, or the platform acceleration, is 2. Gravity is 9.8. The mass of the operator is 85. And so when you put that in, you get this. Now, you get a negative, and the reason for that is because it's negative the direction of acceleration, if you define acceleration to be positive in this direction. So it's a 663 Newton force opposite your direction of acceleration. That's the negative. So if you were asked for the magnitude of that force, it would be 663 newtons. Or you can say 663 newtons opposite the motion of the lift. All right, next one is looking at, again, the same idea as we've seen before. This one looks at something called kilogram weight, though. And kilogram weight is just a fancy way of saying G, like 4G. So when we look at this body of mass 10 kilos on a rough horizontal surface, I'm going to actually draw this one. All right, so we've got a surface. We've got 10 kilos. I don't know what this is. We'll just make it like a box. Ooh. There we go. We'll make this a box. So we've got 10 kilos, 10g. We've got a reaction force, and this is just your weight force. Reaction force here will be 10g. We've got a body of mass is acted on by a horizontal force of 4 kilogram weight. Okay, so we've got the horizontal force is going to provide drive or motion. So that's going to be, I'm just going to make motion in this direction. 4g, this represents g, so it's 4g newtons. And then we have friction. Friction is mu times r. And in this case, we've actually been given mu, the friction coefficient, and we know r because it has to be the same, it has to balance. So let's look at the things that are going on here. If we look at the horizontal action, so the horizontal forces, we've actually got a force F net, the net forces. Let's say in the direction of motion, it's 4g newtons minus 0.2 times 10g newtons, which is 4g minus 2g, so it's 2g newtons overall in that direction. That's your net force. We're being asked to find the acceleration. So as soon as I see acceleration, I think F equals ma, where F is the net force. 2g. Mass, it's 10, but not 10g. Okay, whenever you see mass, it's just the actual mass, not the weight. This is the weight. The mass is 10 kilos. It's just 10. And acceleration. So acceleration is 2g on 10, which is 9.8 times 2, so divided by 10. We can just leave it like that. I probably did it here. Oh yeah, so 1.96. 1.96. So that's for part A. We found those things. And the next thing we need is the velocity of the body after 10 seconds. Now the velocity of the body, again, it's got what's V, it's got time being 10, it starts from rest, it's got suvat written all over it, this one. We know A as well. So we can actually use all the information there. We can use V equals U plus AT, which is U plus A times T, which is 19.6 meters per second. So I've just used, as soon as I read that question, it really says to me it's suvat, and so that's why I use it. All right, cool. This next one here we're going to do, so for the last two questions here, these are a little bit different to the ones we've done before. So we've got a puck of mass 0.1 kilos is sliding in a straight line on an ice rink. So it's 0.1 kilos, so 0.1 g mass, weight force, and a reaction force which is equal because it's not going up and down. And the puck is travelling. Now it's not being pushed, all right? It would have been hit, which means there is no driving force on this anymore. All right, it's actually still moving, and all it's doing is slowing down with a friction force. Now that friction force, remember, is mu r. So in this case, if we look at the net force acting on this puck, we actually have no force pushing. We're not still moving around pushing the puck everywhere, but we have a resistive force, mu times r. Now we know that the coefficient of friction is mu, is 0.025. So we have, 0 minus 0.025 r, which is 0.1 g. So that's our net force. And that's the resistive force. In this case, that's going to be overall. This question here, part A, is actually just asking you for the resistive force. So the resistive force due to friction is just the mu r part, so just this part. And I haven't found the value of that because that's awkward, so I'm just going to have a look at this. So I've got the working here. So we've ended up with this here. So 0.0245. Okay, so 0.0245. So once we've got that mu times r, which I'll write here, oops. We're now going to look at the next thing, which is finding the speed of the puck after 20 seconds if its initial speed is 10 meters per second. Again, this action is saying to me, what's speed? T is 20, U is 0, U is 10. Actually, its initial speed is 10. We need 3 bits of information, right? Now we know the net force is, in this case, negative friction only. We know F equals ma. We know that this force, the net force, equals the mass, which is a 0.1 kilo puck, times the acceleration. So therefore, acceleration is 0.0245 divided by 0.1. And in the worked solutions, we get negative 0.245. Meters per second squared for A. So now we've got time, initial, and acceleration. So we can use v equals u plus at, where u is 10, a is this negative 0.245, and t is 20. And if we multiply all those together, or put them together, we have this thing, and you'll end up with 5.1. And that's meters per second because it's a velocity. So here I've actually done integration. Again, you know what? It would be easier to just use SUVAT. I don't know, integration is a bit more work than you need to do. So SUVAT gives you exactly the same thing. 5.1 meters per second is the velocity. You can see that it started at 10 and it ended up less. And the reason for that is the only force acting on this puck is resistive force, which is why it slows down. The last two questions you've got here are find the acceleration of a 5 kilo mass in the following situations. And these are really easy. Smooth surface means no friction. Okay, so in a situation like that, if you have a driving force, that is the only force operating. So the net force on this 5 kilo mass is 10 newtons. That's it. There's nothing opposing the motion. So F is 10, mass M is 5, A is unknown. Use F equals ma, find A. This one, you've got a friction force. Remember that friction force is R, which in this case is 5G, times mu, which is our coefficient of friction. So F of R here is 5G, which I found to be 49, times 0.3, which gives me 14.7. So 14.7 is the friction force going backwards, opposite the direction of motion, which is 20. So the net force is 20 minus the friction of 14.7, so 5.3 Newton force in the positive direction or in the direction of motion. And F equals ma, you chuck in the F, you chuck in the 5 for the mass, and then you find A, and it's 1.06 meters per second squared. So this section was all about using F equals ma. You've got some questions at the end of both B and A to work on, so if you could please work on that, that'd be fantastic, and make sure you've got all your notes filled out. Work solutions are on Canvas.